pleasure to me to present the talk joined with Zafar Haidarov from Samarkand State University, entitled Structure of Resonant Variety in Hamiltonian Systems with 3 degrees of freedom. Here is the outline of our talk. This talk consists of 2 parts. The first one is devoted to the motivation problem setting, and the second part presents the main results obtained during the investigation. I want to mention that this talk is based on our papers with the following references. The first one has been published in Computational Mathematics and Mathematical Physics at the beginning of this year, and another one, which is the extended version of this talk, will be published in Programming and Computer Software Journal. Well, let's start from the first part, and in this part we recall some facts from the stability theory in general, and in particular in the Hamiltonian case. And for theoretical mechanical problems, usually considered 3 types of stability: so-called Lyapunov stability, due to the famous works of Russian mathematicians Alexei Mikhailovich Lyapunov; formal stability, which was provided by Jürgen Moser, one of the co-authors of the well-known KAM theory; and the practical stability. Definitions and explanations of these types of stability is given at the bottom of this transparency, and we concentrate our attention on the formal stability investigation, which is, from practical point of view, is sufficient type of stability for many theoretical mechanical problems. Well, we consider a Hamiltonian system in a general case, which can be presented by the corresponding Hamiltonian function h of z, and we consider that this system has a stationary point at the origin, so the Hamiltonian function can be expanded into a convergent series of homogeneous polynomials in the form 1, which starts with a quadratic form, and our Hamiltonian depends on a vector p of parameters. In a general case, the quadratic part of our Hamiltonian defines the local dynamics in the vicinity of stationary point, and the first approximation can be described with the help of the linear Hamiltonian system in the form 2. Here B of P is the matrix depends only on vector of parameters. Capital G is so-called symplectic unit matrix, skew symmetric, and let me recall some facts from the linear Hamiltonian system. First of all, I want to recall that all the eigenvalues of our matrix B, number of eigenvalues is 2 times n, where n is the number of degrees of freedom, can be reordered in such way, and we in the following use the notation of vector boldface lambda and call this vector the set of basic eigenvalues. Well, the characteristic polynomial of matrix B contains only even pairs of lambda, so the order of this polynomial can be reduced twice. And in following we will use only so-called semi-characteristic polynomial, which coefficients are functions, maybe polynomial functions in parameters capital P. Well, it's a well-known fact that if for some index j the real part of lambda is not equal to 0, this point is called hyperbolic, and this stationary point is unstable. And when all eigenvalues has 0 real part of them, the behavior of S flow we cannot investigate only using the linear part. We have to take into account non-linear terms. It usually can be performed using KM theory, or in this work we use a Hamiltonian normal form. We will use some definitions. The first one is definition of stability set of the linear system 2. It's the set of all values of parameters P where for which stationary point at the origin is Lyapunov stable. In terms of roots of semi-characteristic polynomial 3, the conditions on stability of stationary point can be given by the following theorem provided in such references. This linear system is Lyapunov stable if and only if all the roots of semi-characteristic polynomial are real and non-positive, and all elementary divisors of matrix B are simple. Condition on reality and non-positivity of roots can be formulated in terms of so-called subdiscriminants of a polynomial, and it's a well-known object in the modern elimination theory. Well, let me recall some facts from theory of normal form of Hamiltonian system. First of all, I want to mention that the idea of reducing initial system of ordinary differential equation into its normal form is idea presented by Henri Poincaré. Even though normal form is such a kind of formal object, it can be used for solving the following problem: for finding first integrals, for searching families of periodic solution, for investigating integrability, stability, and bifurcations of stationary points. It can be computed not only in the vicinity of stationary point, but in the vicinity of any invariant manifold of our system. According to the theorem 12 presented in this paper by Professor Alexander Bruno, there exists a canonical transformation in the form of power series which reduces the initial system 1 into the normal form, which described by normalized Hamiltonian small h, consisting of two parts: from quadratic part, which correspond to linear normal form, and terms of high order, which contain only resonant terms, which vector power exponents p and q correspond to so-called resonant equation. There are two types of resonant terms. The first one is called secular, and this type of terms always present in our system due to specific type of Hamiltonian system, and the other type of resonant terms are called strong resonant, and they can be presented only in the case of the existence of resonance. Well, here you are a list of several methods of truncating initial system into its normal form with the corresponding references, and I want to say that our investigation based on a scheme of formal stability investigation presented in the following paper, which is based on such assumptions. Well, this scheme is a good scheme for the case of degree of freedom no greater than 2, and for generic case, but for systems with degrees of freedom 3 and more, it cannot be applied directly, and has to be adapted for this case. Well, here is a definition of the formal stability, and we will use some definition of resonance properties. Resonance multiplicity is a number of linearly independent solutions of resonant equation in such form. Resonance order is the minimal value of the norm of vector exponents p satisfying resonant equation. If only two eigenvalues to take part in this equation, we will call this type of resonance two-frequency resonance. In other cases, 3 or more eigenvalues take part in this equation. We will call this multi-frequency resonance. And finally, this type, these resonances of orders 2, 3, or 4 are called strong resonances. Condition capital A Kn for the system with n degree of freedoms describe the situation when our system does not have strong resonances of order less or equal k. Well, in terms of condition A sub 4, we can reduce our Hamiltonian in the following form. Here is a quadratic part written in action angle variables, and here is a quartic part of our polynomial, which can be in these variables written as a quadratic form. And finally, the key result for formal stability investigation formulated in the theorem, which is called theorem by Bruno on formal stability condition. To apply this theorem, we have to find all parts in the set of parameter space where strong resonances do not exist. So the problem that we try to solve is the following. We try to describe varieties, so-called resonant varieties, corresponding to strong resonances defined by the integer vector p. And in the case of 3 degrees of freedom, we have the following list of our vector p resonances. We consider the case of 2 frequency resonances and consider the case of 3 frequency resonances. So finally, to solve the problem of formal stability, we should obtain description of boundaries of regions which are free of strong resonances. And to understand the structure of these boundaries, we have to obtain the analytic representation in the coefficient space of semi-characteristic polynomial of resonant varieties handwritten R sub 3p for all vectors p corresponding to strong resonances, and to find mutual location of all resonant varieties, which is described above. In the second part of the talk, we'll provide the results of our computation for the Hamiltonian system of 3 degrees of freedom in a general case. Well, let's consider 2 ways of computing the condition of existence of resonant relations for a given resonant vector p star. The first method provides us with the implicit representation of the resonant variety, and the second method allows to obtain parametric representation. Both methods starts with the computation of the resonant relation between the roots of the semi-characteristic polynomial for a given resonant vector p star. So let's consider our vector in the following form, where variables r and q are integers, and we compose a polynomial ideal capital handwritten J, which consists of the resonant equation and which consists of a set of relations between the basic engine values and the corresponding roots of semi-characteristic polynomial. After that, for this ideal, we compute Grobner basis with a certain elimination monomial order, and the first polynomial of this Grobner basis provide us with the condition of existence of the resonance with the following resonant vector in the following form. This is a form, this quadratic form of 3 roots m1, m2, and 3 with the coefficients depends on the integer values r and q. This is a quasi-homogeneous polynomial, to obtain this condition in the terms of coefficients of our polynomial, we have to construct another one Grobner basis of the ideal, and this ideal contains the obtained condition at the previous step here, and we add a set of elementary symmetric polynomials which connects the coefficients of our polynomial and their roots. In this case, we specify elimination order of variable. First of all, we try to eliminate our variable mu j, which denotes the roots, and then we eliminate the coefficients. After that we obtain condition in terms of our coefficients. So the obtained polynomial is quasi-homogeneous. To each monomial we can put into accordance its vector power exponent, and so each monomial will correspond to a point in a space of vector power exponents, and this point lies on the plane with a normal vector n with coordinates 1, 2, 3. So it made possible to reduce the number of variables of this polynomial by 1 and obtain our condition in the form of a plain algebraic curve. But this method turns out to be very time consuming, and it cannot be expanded to the situation with the number degrees of freedom greater than 3. For condition which we obtain on the first step, we can apply a corresponding power transformation written here and obtain in new variables S1, S2 the following algebraic curve of genus 0 with the following polynomial parametric representation. So our roots can be written in the following polynomials, where u and v is the free variables, r and q are coordinates of our resonant vectors. And after substitution in the elementary symmetric polynomial, we obtain the following polynomial representation of our variety, which describe in three-dimensional space a resonant variety as a smooth surface with singularities. If we exclude from this parametrization free variables u and v, we can obtain implicit representation of our resonant variety, but this expression cannot be written on this transparency due to its cumbersomeness, and this quasi-homogeneous polynomial consists of 19 monomials with a huge coefficients from the components of vector p star. Comparison of these two methods skip, and we want to say that all these computations were provided with the help of computer algebra system Maple, where we use a package for Gröbner-based computation and use the package alcurves, which provide us with a very great procedures computing genus and rational parametrization of algebraic curves. Let's consider a special case for two-frequency resonance, which was earlier considered in my paper with the help of Q elimination theory. I just recall briefly the main steps of our computation. So if we have two-frequency resonance between two eigenvalues lambda 1 and lambda 2, it can be written in the form of the linear form between the roots mu1, mu2, and adding our symmetric elementary symmetric polynomials, we obtain a polynomial ideal. Excluding mu1, mu2, mu3 variables, we obtain our implicit representation of resonant variety of two-frequency resonance, and here a few pictures which show us its situation when we have two equal eigenvalues, and the third eigenvalues is an arbitrary non-consumable. And here is a discriminant of the cubic polynomial, monic cubic polynomial, and our resonant variety is such a smooth surface with a singularity depicted with a red curve. And here is a picture of resonant variety of order 3 and 4 corresponding. They are similar, so this is a picture of this one. And here is a smooth variety with singularity depicted with the red curve. And here is an animation of a mutual location, mutual position of these varieties. Well, let's go to the situation of three frequency resonances. I want to stress your attention for, in this case, we have to distinguish two situations when our resonance has multiplicity 1. Here is an example, and multiplicity 2. We consider only resonances with multiplicity 1, because the case of multiplicity 2 can be solved with the help of two frequency resonances. Well, consider the case of resonance with the resonance vector 1, 1, 1. We obtain in terms of mu roots the following quadratic form, and in terms of coefficient it will give us such a kind of surface. It's a parabolic cylinder. For resonance 2, 1, 1, it's more complicated case. After following certain steps, we obtain such a kind of implicit representation of these resonant surfaces, and both polynomial are quasi homogeneous, so we can apply power transformation in the form 9, and we can reduce the dimension of our varieties from 3 to 2, obtain them in the form of algebraic curves, and compute polynomial parametrization of these curves. Here is the polynomial parametrization of the two frequency resonances, and here is the polynomial parametrization of three frequency resonances. And here is a picture which gives us the mutual location of our resonant varieties in new variables mu1, mu2. Black curve corresponds to discriminant surface, and this curvilinear triangle gives us a domain in the set in our where our semi-characteristic polynomial has negative and real and negative roots. So it corresponds to a situation of the linear stability. Blue curve L2 L sub 2 and green curve L sub 3 correspond to two frequency resonances. Purple and red correspond to three frequency resonances of order 3 and 4 correspondingly. And red points denote situation when the multiplicity of these resonances increased from 1 to 2. So we have more than one solution, or more than one solution, or solutions of our resonant equation. Well, here is a short description, written description of this situation, and this general theory was applied to a mechanical systems or non-trivial example with 3 degrees of freedom and 2 parameters of 3 almost sympathetic pendulums which connected with the springs, massless springs, and in the set of parameters we obtain our varieties, resonant varieties, which divide the plane of parameters into different parts. For details, see our preprint and see our paper, which was mentioned on the first slide. Well, it's a final conclusion which states that for the Hamiltonian system with 3 degrees of freedom, we can obtain the description of partition of the set of stability in the coefficient space of semi-characteristic polynomial into parts where the strong resonances are absent, and we can apply Bruneau theorem on formal stability. And last but not least acknowledgement, we want to express our gratitude to Professor Alexandrovich Bruneau for helpful discussion of this work. Here is a list of references which mentioned in this presentation, and finally we want to thank the audience for their attention. Thank you very much.